let us discuss quantum theory of Raman effect. The quantum theory of Raman scattering describes how light and molecules interact to produce inelastic light scattering. This interaction can cause the scattered light to have a different frequency than the incident light. When light hits a molecule, it can either scatter elastically or inelastically. During inelastic scattering, the energy of the scattered photon is different from the energy of the incident photon. This is because the photon can add or subtract energy from the molecule. In quantum mechanics, the scattering involves alternations in particle trajectories or states during interaction, and it is essential for understanding the phenomena like particle accelerations and light scattered by atoms. Raman spectroscopy is a technique that uses the Raman effect to study the structure and properties of materials. It is used in material science and pharmaceuticals. The occurrence of Raman scattering is understood easily by means of quantum theory of radiation. This treats radiation as frequency nu as consisting of a stream of particles, which is nothing but photons, having energy h nu, where h is the Planck's constant. Photons are imagined to undergo collisions with the molecules. If there is no exchange of energy between the photons and molecules, that collision is perfectly elastic. This scattering is known as Rayleigh scattering. Whereas, if the energy is exchanged between the photon and the molecule during the collision, then this scattering is known as Raman scattering. Hence, the molecule can gain or lose energy equal to the energy difference del E between any two of its allowed states. Del E represents a change in the vibrational or rotational energy of the molecule. If the molecule gains the energy, the photon will be scattered with the energy h nu minus del nu. It is known as Stokes scattering. On the other hand, if the molecule loses the energy, the photon will be scattered with the energy h nu plus del nu. It is known as anti-stokes scattering. It is pointed out that the annihilation of the incident photon and the creation of the scattered photon are simultaneous. The intensity of a spectral line depends on the initial population of the state from which the transition originates. Stokes radiation is generally more intense than the anti-Stokes radiation. However, the total radiation is weak, hence the sensitive apparatus is required for its study. The pictorial diagram of Raman scattering is as shown here. So this is the picture of Rayleigh scattering, Stokes and the anti-Stokes line. And this line represents the energy. And we have the ground state here, over which we have vibration energy levels. So there are many more vibration energy levels exist. So n equal to 0, n equal to 1, n equal to 2, n equal to 3, and goes on. And here we have below the excited states, we have virtual states. Suppose if there is no energy loss, and gain, and what we call this is Rayleigh scattering. But here the energy transfers from ground state to the one of the virtual states here, and it comes back not to the ground level, whereas it comes to the one of the vibration energy levels. So here, and this is known as Stokes line. And already the molecule has some energy due to vibration or due to rotation, and it will be in any one of the vibration energy levels, and it goes to the one of the virtual states and comes to the ground state, and this is known as anti-Stokes line. And together, Stokes line and anti-Stokes lines together, what we call this as Raman scattering. So Stokes energy is nothing but transferring a part of light photon energy to the molecule gives rise to the Stokes line. Here, E scattering is less than that of E incident. So H nu S, S stands for Stokes. So we have H nu S equal to H nu excitation minus H nu naught. And here this is your H, not H bar, it is H. New photon appears with energy smaller than the exciting energy. Whereas in anti-Stokes scattering, we have the molecules in an excited vibrational state prior to the irradiation gives rise to the anti-Stokes line. But here E scattering is greater than that of E incident. So we have H nu anti-Stokes line which is equal to H nu excitation plus H nu naught. Here the emitted photon has larger energy than the excited. Energy increase or decrease is related to the vibration energy spacing in the ground state. Let m be the mass of the molecule. Nu I and nu S its velocities before and after the impact. E1 and E2 are the intrinsic energies of the molecule before and after collisions. And nu I is the frequency of the incident photon and nu S is the frequency of the scattered photon. Then applying the principle of conservation of energy, we have E2 plus 1 by 2, that is half mv2 square plus H nu I, which is equal to E1 plus half mv1 square plus H nu S. Let us assume that the kinetic energy of the molecule remains the same during the collision. Hence, we have E2 plus H nu I, which is equal to E1 plus H nu S. So you bring H nu I that side. We have taking the H common out. We have H times nu S minus nu I, which is equal to E1 minus E2. So we bring the term H here. Then we have nu S minus nu I, which is equal to E1 minus E2 divided by H. And nu S minus nu I is known as Raman shift. And this equation represents the unmodified line. So nu S equal to nu I plus E1 minus E2 divided by H. So you bring nu I to that side, we will have this equation 3.16. Now from equation 3.16, we can have three cases. So this is the equation nu S equal to nu I plus E1 minus E2 by H. The first case, it is nothing but Rayleigh scattering. Photons, radiation of frequency and energy are imagined to undergo collisions with the molecules. If the collision is perfectly elastic, there is no net gain or loss of energy by the molecule. When there is no change in the energy of the molecule, we have E1 equals E2. So therefore, nu I, which is equal to nu S, where nu I is the frequency of the incident wave, nu S the frequency of the scattered wave. The energy of the scattered radiation is equal to the energy of the incident radiation. That is, change in energy is 0. So therefore, del E equals 0. Case 2, which is nothing but Stokes line. There will be energy exchange between the molecule and the incident radiation. This elastic collision is known as Raman scattering. Here, E1 is not equal to E2. That is, del E is not equal to 0. It will be positive or negative depending on how the energy is exchanged between the photon and the molecule. Whether the photon has given energy to the molecule or the molecule is given energy to the photon, depending on the situation, del E can be positive or negative. So in this case, in the case of Stokes line, if E2 is greater than that of E1, that is, then nu S is less than that of nu I. This represents the Stokes line. It means that the molecule has absorbed some energy from the incident photon. The molecule relaxes from the virtual level to a higher level than the original. Consequently, the incident photon has lower energy or longer wavelength. Case 3, this is nothing but anti-Stokes line. In this case, we have E2 less than that of E1. Then nu S greater than that of nu I. This represents the anti-Stokes line. It means that the molecule was precisely in the excited state earlier, and it handed over some of its intrinsic energy to the incident photon. Thus, the scattered photon has higher energy or shorter wavelength. Since the molecules possess quantized energy levels, we can have E1 minus E2, which is equal to NH nu C, where nu C is the characteristic frequency of the molecule and n equals 0, 1, 2, 3 goes on. In the simplest case, when n equal to 0, equation 3.14. So this is equation 3.14. E2 plus h nu s equal to E1 plus h nu I. So from this equation 3.14, we can have nu s equal to nu I plus E1 minus E2 by h. And this is equation 3.15. So E1 minus E2 equal to NH nu C. Suppose if n equal to 1, we have E1 minus E2 can be written as nu C. So substitute here. So we have h nu C, h s get cancelled, we have nu C. So nu s equal to nu I plus nu C. So this can be written as equation 3.18. So equation 3.15 shows that frequency difference nu s minus nu I between the incident and scattered photon corresponding to the characteristic frequency nu C of the molecule. And the incident light, when it falls on molecule here, some other molecules, sample molecules here, we have inelastic scattering as well as elastic scattering. So we have Rayleigh lines and Raman scattering. So look at the color. We have the same color which is coming out, which is nothing but your Rayleigh line. And we have Stokes line, and look at the line. We see this is red color, and anti-Stokes line we have more energy, high frequency. See here anti-Stokes line, and this is lower wavelength. Anti-Stokes lines will have lower wavelength, and Stokes line will have higher wavelength and low energy and low frequency. Factors influencing intensity of Raman lines. Intensity of Raman lines is directly proportional to the intensity of the light source. Intensity of Raman lines is inversely proportional to the fourth power of the wavelength of the source. Intensity of Raman lines increases with temperature. It depends on the concentration of the sample or number of molecules. It depends on the scattering properties of the sample. And this picture represents Rayleigh, Stokes and anti-Stokes lines. And as we discussed, these levels are vibrational energy levels here, this one, and we have virtual state levels are here. And for Rayleigh scattering, as you know, this is inelastic scattering in which no energy is lost. This is for Rayleigh scattering, and of course this is for Stokes line, and this is for anti-Stokes lines, and subsequently we will look at each picture elaborately. First one is Rayleigh line. So in Rayleigh scattering, we have during the collision, if the incident energy takes up some energy from the molecule, then the scattered radiation will be more energetic. The excited molecule from the virtual level relaxes to the original level. So nu s is equal to nu I, and A prime molecule minus E molecule, there is change of energy, which is nothing but del E, which is equal to 0 in Rayleigh line, Rayleigh scattering. Whereas in Stokes line, we have during the collision, if the incident energy takes up some energy from the molecule, then the scattered radiation will be more energetic. The excited molecule from the virtual level relaxes to one of the vibration energy levels. So in this case, we have nu s is less than that of nu I. So we have E dash molecule minus E molecule, that is change in energy is nothing but positive value. Del E is greater than 0. And in anti-Stokes line, during the collision, if the incident energy takes up some energy from the molecule, which is already in any one of the vibration energy levels, then the scattered radiation will be more energetic. The molecule relaxes from the virtual state level to the lower level than the original. So we have mu s is greater than of mu I. So here A dash molecule minus energy of the molecule, which is equal to change in energy of the molecule is nothing but negative value del E is less than that of 0. Raman shift. The difference in the frequencies of the Rayleigh line and the Raman line, which is nothing but del nu, which is equal to nu I minus nu S, is referred as Raman shift or Raman frequency. The picture shows the intensity variation with the frequency. And of course, Rayleigh scattering is very high intensity and Raman scattering is weak intensity. So it is shown here. So they are all weak intensities, Stokes and anti-Stokes. And of course, at the center we have the Rayleigh scattering, which is high, which has a high intensity here. The Stokes and anti-Stokes lines together, known as Raman lines, will be situated on either side of the Rayleigh line. That is nu S equal to plus or minus del nu. Here, plus stands for the Stokes line and minus stands for the anti-Stokes lines. Stokes radiation occurs at lower energy, that is longer wavelength, than the Rayleigh radiation, and anti-Stokes radiation has greater energy. The increase or decrease of energy is related to the vibrational energy levels in the ground electronic state of the molecule. The observed Raman shift of the Stokes and anti-Stokes features is a direct measure of the vibrational energies of the molecule. For a given substance, the Raman shift is the characteristics of the substance and independent of the frequency of the intensity of the radiation. Intensity of Stokes and anti-Stokes lines. The intensity depends on the population of the energy levels. Greater population, greater will be the intensity of the spectral line. Look at the Rayleigh scattering. This is inelastic scattering in which there is no loss of energy and most probable transition and hence more intensity. So Rayleigh scattering will be much more intense. At ordinary temperature, most of the molecules will be in the ground state. And of course, Stokes line will have less intense than that of Rayleigh scattering, and anti-Stokes will have very, very less intense that of Stokes line. So Stokes emission is more favored than anti-Stokes emission. Hence, Stokes lines will be more intense than anti-Stokes line. Population in the ground state of Stokes lines is greater than that of the population of the excited level of vibration level of anti-Stokes line. The intensity of lines varies in the order as Rayleigh line is greater than that of Stokes line, which is greater than that of anti-Stokes line. So anti-Stokes line will have less intensity and Stokes line will have more intense that of anti-Stokes, and of course Rayleigh scattering will have more intense than the Stokes and anti-Stokes lines.